And we ended up with talking about a specific example related to strontium-ruthenate, and that's looking at the point group D4H. And I showed you the 5 representations here and pointed out that the Ginzburg-Landau theory for these 4 representations is identical. So they're all the same as the usual Ginzburg-Landau theory, but the Ginzburg-Landau theory in this case is different. And so we looked at the Ginzburg-Landau theory for this case. The only thing I forgot to mention yesterday, which I should mention, is that these Ginzburg-Landau theories are, of course, only well defined if they're bounded to load. So if I take any choice of eta, this free energy has to have a lower bound. It can't run off to minus infinity. If it runs off to minus infinity, I have to add more terms to this to make sure it does stay bounded to load. So it's one thing I neglected to mention, although it was implied. All right, and so then we looked at this particular example here, and then in principle you can minimize this. And I told you, which was the very end of the lecture, that there are 3 possible phases that come out, right? So you get this 1I phase, this 1 phase, and this 1, 0. So 1I is px plus ipy, this is px plus py, and this is just px. And then these phases have zeros of the gap on the Fermi surface. This phase has no zeros of the gap on the Fermi surface. And so the next question we wanted to ask was, since we have 3 possible ground states, and the properties of ground states are quite different, how can we determine which one of these actually occur in nature? And one nice feature we have is we have a microscopic theory that allows us, in principle, to calculate these coefficients. And so the next task was to answer the question, what possible ground states can we have in weak coupling theories of superconductivity? So that's where we'll start. Oh, and I gave a homework problem. I don't know, did anybody do it? Well, that's true. I didn't say a deadline for one. No, but anyone, well, if anybody, sorry?
It wasn't graded.
It wasn't graded, yeah. Well, if anybody does do it and they want to know the answer, I can tell. I'll leave it up there. All right. Oh, yes.
Can I ask you
Sure.
a very ignorant question? Px plus ipy, you say, is that just a name, or does
That's a name for
that
this character.
combination that number stand for?
Px plus ipy.
Yeah.
I mean, I haven't actually completely defined it yet, and I will in a little while. But as you'll see when we go through the microscopic theory, spin triplet superconductors, which means odd in momentum, are described by a vector corresponding to the spin degree of freedom, and then have momentum dependence. And then, well, okay, maybe I think this is px plus ipy. So this corresponds to the structure on the Fermi surface. I should use kx plus iky. K defines the points on the Fermi surface. Yeah, so as I go around the Fermi surface, it has this phase coming from the kx plus iky. So you can imagine a cylinder. It's just a phase, e to the I theta, as we move around the cylinder. And then these other phases, this one down here, would simply be px plus py, and the other one would be px, and then px is the easiest to draw. If I draw a 2-dimensional Fermi surface, then px would be, say, plus here, minus here, and there would be zeros here and here on the Fermi surface. So again, this is where the gap is biggest and positive. This is where the gap is also biggest and negative. Then the gap vanishes here and here. I haven't drawn the picture exactly right. I should draw the lobes coming to these points, right? And then I don't know how to draw a complex function other than drawing little arrows here for one to around there. So I won't draw px with something else. All right. So let's So these are very pedagogical lectures. Okay. I don't know if you missed the first one, so we might.
I just want to sit here and say anything.
I'm just apologizing if it's difficult to follow. All right. So the goal now is to find out this free energy from weak coupling BCS type theory, and so I'm going to really not go through a lot of details here, but really sketch how this is done. And I'm going to do it through 2 steps. Right? So the first thing will be, I'm going to talk about the mean field theories. But what's nice about the mean field theories is we can, from the mean field directly, understand the symmetry properties of this gap function and how they change under all kinds of rotations. And we'll see that in some detail in a second. And from that alone, we can understand much of what we need to talk about. And then I'm going to go further and talk about the solutions of the mean field theory, which maybe all of you already know, but then show you how you go specifically from that to the Ginzburg-Landau free energy that I talked about before. All right, so all I have here is a kinetic energy, and here I have a pairing energy. So here's a Cooper pair at point K getting scattered to a Cooper pair at point K prime on the Fermi surface. And then we have a bunch of spin indices here. All right, and so for those of you who haven't done mean field theories, all we do is the following. We take, if I look at, for example, let 1 and 2 label my K and minus K and S prime. We simply write that as a mean field term plus a fluctuation term. And then what we do is we take, for each of these C daggers, and these CCs, we put this in, and we throw out the product of these 2 fluctuation terms. And so when we do that, we end up with terms that are C dagger, terms that are CC, and also a constant term, these expectation values. And so I've also absorbed expectation values and V's into this gap function delta, and that's written down here. Okay. So everyone see how we get this mean field Hamiltonian from here? I think it's something many of you have seen anyhow. The point is now that we have something that we can solve exactly because it's quadratic in the fermion operators. And what's going to be of interest for us then in particular is the self-consistency equation. You can solve this Hamiltonian exactly, you can find out what this expectation value is, and then this is going to depend itself on delta, and so we'll have a self-consistency relationship for delta. Right. But now that we have the mean field theory, we can actually, I want to say one more thing before I go on. So this is our gap equation, and the important thing is that fermions obey Pauli exclusion. That means under the interchange of these 2 operators, I must pick up a minus sign, right? And so to compensate for that, I have 2 possible, I have a K dependence for my gap and a spin dependence for my gap. And interchanging the 2 fermions will take K to minus K or interchange the 2 spin indices. And if I have a system that has parity symmetry, then I'm always allowed to classify my eigenstates according to parity symmetry with either positive or negative parity eigenstates. And so in a system with parity symmetry, I can get a nice simple classification of my gaps, because if I require my gap function to be even under parity, so here I have function psi of k that goes to psi of minus k, Pauli exclusion automatically implies that I must be asymmetric in the spin indices. And so I get this nice classification that even parity symmetric functions must be spin singlet. And then conversely, if I have something that is odd in parity, so something that changes sign under k goes to minus k, then I get something that must be symmetric in the spin indices. And so that'll be a spin triplet. We'll get 3 spin triplet states and 1 spin singlet. And so I emphasize the role of parity because, as many of you know, a lot of condensed matter physics right now is interested in states without parity or without inversion symmetry. And there are many examples. And so it's worthwhile pointing out we get this nice classification. Spin singlet is even parity, spin triplet is odd parity, only when we have parity as a true operator for Hamiltonian, or that commutes for Hamiltonian. All right, so I skipped over a bunch of other details here, but at least in the spin singlet case, I can describe that now by a scalar psi of k, and this corresponds to pairing the up-up, up-down, down-down, and down-up channels. And so a spin singlet will be up-down minus down-up. And so that gives me that completely characterizes my spin singlet pairing states. And so we'll talk about these scalar functions psi of k, and that'll classify spin singlet pairing states. Conversely, for spin triplet, I now need something that is symmetric, and so in particular this off-diagonal component must be equal, right? The up, down, and down, up must be equal. And you notice I write this in a sort of peculiar form, right? I have this three components, dx, dy, and dz, and then I write this component minus dx plus I dy. And there's a very good reason for that. When you look at how, if you apply a spin rotation to the system, it turns out this vector d rotates as a vector under those spin rotations. And so its symmetry properties are very easy to understand because of that. So that's why this notation is chosen. D rotates as a vector if I rotate all the spins of the single particles the same way. All right, so I'll be talking about even parity and odd parity, and then carrying along with that will be the spin singlet and spin triplet. So I'll be assuming that all my systems have parity symmetry in the following. All right, so let's get to the first conclusion we can make. We have a mean field Hamiltonian, and in the mean field Hamiltonian we've introduced our pairing symmetry. But now we can ask the question, suppose we know there's some symmetry that our Hamiltonian has to obey. And that means that if I apply the symmetry operation G dagger HG, that must be equal to H. From this, do you have a question? Or no?
About the previous slide.
Previous slide, okay. Yeah.
In the second case, you couple the spin and orbital motion to the zero total angular momentum, correct?
Not necessarily. So here, this is just a function of k. There's nothing, and so d characterizes the spin degrees of freedom. In fact, what I'll talk about later will have no spin orbit coupling just to make it simple.
So they are uncoupled. Each of them is separately conserved.
So in reality, no. But when I talk about we'll get to that in a little bit.
The reason is because you can have different couplings. You see, you can couple to 0, 1, or 2.
Yes,
right?
exactly.
Or not couple at all, and you obtain different solutions. So.
That's true. I mean,
So
if you just imagine p wave in a spherical system, there's 3 degrees of freedom for k vector, then there's 3 degrees of freedom for the spin vector. So you have 9 degrees of freedom, which is a lot. But then again, you can add spin orbit coupling and you can break that up, as you said, into 3-dimensional representation, I guess a 2-dimensional, a 1-dimensional, I must be missing one. A 5-dimensional, 3-dimensional, 1-dimensional, that's right, yes.
It's 0 to spin.
Exactly.
So here you don't have any spin orbit coupling.
Well, I'll talk about that. So you can, of course, do theories with and without spin orbit coupling, right? All right. In fact, you'll see, it'll come up in the next couple slides. All right. So, the point I'm making is that we can apply these group transformations to the Hamiltonian, and we also know how these individual electron operators transform under these rotations, and therefore we can deduce how this gap function must transform under these rotations. All right, and so, let's look at that. Let's figure out how these gap functions transform under particular rotations of interest. All right, and so the symmetry operations that will be of interest are orbital rotation, and we're going to consider spin rotation separately for now. So here's the answer to your comment. Right. Then we'll also talk about time reversal symmetry, and I'll also apply U1 gauge transformations, just multiplying the electronic creation annihilation operators by a phase factor. All right, and so here are the rules. So for people who are looking at this particular line here, I'm considering only s orbitals for simplicity, right? There can be some more complicated structure here, but I'm just imagining that we're starting with some set of s orbitals because we can otherwise, I can't make this as... So, we know how to do this for more general cases, but for now let's consider s orbitals. Right. So an orbital rotation, what it will do then for these s orbitals is it'll just rotate the k vector like a vector. Right. A spin rotation, well, we're going to assume again spin 1/2, and so then the spin rotation will pick up these combinations of spins, but you've all seen this spin rotation operator before, and these are the Pauli matrices showing up here, and then this is the angle orthogonal to the rotation axis. Time reversal, it's an anti-unitary operator, which I haven't actually spelled out here other than writing it, but what it does is, in essence, it changes the sign of k and changes the sign of spin. Now there's a non-trivial phase factor that shows up in there as well, but I'm not going to be talking about that. Just remember, it changes k and spin, and that's sufficient for most of what will happen, and it's anti-unitary.
But you assume that the functions are real, because you need a complex conjugation.
Yeah. So yes, you're right. But that's in a system with time reversal and parity symmetries in the ground state, you can choose basis functions that are real. So it's not in essence.
Well, if you break time reversal invariance, you're wrong. Don't.
Yeah, but we're talking about the normal state symmetry operations and then phase transitions out of that. So then we're okay. So here I'm talking about normal state operations, and we can worry about what happens after that. And you'll see, I will include the complex conjugation later, but I haven't spelled through the details of that. All right, and then finally we can apply a U1 gauge transformation, and for convenience here, I apply this operation. The electron operators pick up a factor e to the I5, I2. And the reason I do this is because I'm going to be looking at Cooper pairs where I wanted to pick up a factor e to the I5. All right, so we know these symmetry operations. We can now, from the single electron operations, deduce what must be the operations on the mean field Hamiltonian, in particular on the gaps. And so I'll just tell you the answers in this case here. So again, I'm looking at the singlet cases where I have the scalar psi of k, and also the spin triplet cases where I have a vector d, which is odd under k, right? So this is odd parity, this is even parity. So that tells you the parity. All right, and so in this particular case then, an orbital rotation, again, simply rotates k for both of these, and also for the spin case, it just rotates the k vector. If we have spin orbit coupling, well, okay, let me first talk about spin rotations. Spin rotations do nothing to the spin singlet state because it's a spin zero object, but then it rotates the d vector as a vector, and so this is just a 3x3 rotation matrix here, corresponding to the rotation. Time reversal takes the complex conjugate, but then takes k to k, actually, if you go through everything carefully. So it, in essence, just takes the complex conjugate of both the singlet part and the triplet part, and I'll talk about that in a couple seconds. And the gauge transformation, not surprisingly, gives a factor e to the I5 for the singlet and the triplet components. All right, and then again, if you have spin orbit coupling, then you have to make these two operations the same, and then the d vector has the same r here and the same r showing up here. In fact, that's what this is saying. But like I said, for simplicity, I'm only going to consider things without spin orbit coupling. Okay, so. So let me show you what I mean about how we can use this information. So let's look in particular at the spin singlet case under rotations. We know that under a rotation then, psi of k goes to psi of the rotated k. All right. And this is a 3x3 rotation matrix. And now let's go back to our character table for D4, all right? And let's look in particular at one of the representations. Let's look at B1. Let's look at this representation here. And let's ask the following question. So you guys may be familiar with this B1 representation. So if I draw a cylindrical Fermi surface, then you guys may have seen the following picture for a D-wave order parameter. Right, and so here's some particular choice, and this belongs to the this B1 representation. In particular, if you look under fourfold rotation, I should pick up a minus sign, and indeed, if I rotate, can everyone see this actually? Yeah. So under fourfold rotation, this plus goes to minus, so I pick up a minus sign indeed. And then under this twofold rotation here, I also pick up a minus sign, and if you remember, that twofold axis was this axis here, so I pick up a minus sign. All right, so what I showed you here is a particular single example of a gap function, but the problem is I told you yesterday that there's an infinite number of choices of gap functions we can make, right? Any one of these can be equivalent basis functions, and I showed you a couple pictures of that. And so what you want to do is, if you look at this picture, maybe I forgot to mention the main point, you notice that it vanishes at these points here. And you want to answer the question, does it vanish for all possible gap functions? And you guys know the answer is going to be yes. But how do you show that? You show that by the definition of the representation combined with this transformation rule. All right, and so then, show you how that's done. So, we know if it belongs to this B1 channel, then under, and I'm going to, let me just use the same symmetry operation I have here. Yeah. Let's choose this twofold rotation about this axis here, all right? That's the non-trivial one. Under this operation, from the definition, we know this must pick up a minus sign, right? But also, we know how it must transform under this operation. So we know, in particular, if we choose, well, we know that psi b1 of k goes to psi b1 of rk. And so now, you can see that if I choose a vector k such that under the rotation I get back the same vector, then I must have this thing vanish, right? Then I'll get psi of k, so by this rule here, it'll vanish. I'll get the same side. Right. So, in particular, if k equals r of k for this particular rotation here, then I'm required that psi of k vanishes. Does everyone see that? Okay. And so you can see which vectors that is, right? So under this twofold rotation axis, exactly this vector doesn't change under rotation, and that tells me I must have my nodes here. So you can use the definitions of the representations combined with this transformation rule to tell you where the nodes are. And so this is true for all basis functions as long as it belongs to that representation. All right. And the second thing I wanted to mention about this is the property of time reversal. So if you look at the time reversal operation, it takes the complex conjugate of both of these. But if you look at parity, parity just takes, for one case, it's even parity, for the other case, it's odd parity, right? And so under parity, here you get opposite signs. And in principle, Ginzburg-Landau theory allows the possibility that under time reversal, you not just take the complex conjugate, but you get the negative as well. And so you might ask, where are these states? These states don't appear within this definition of our, or within the symmetry properties of the gap functions we found. And in fact, it turns out that these are actually very well studied in a very different language. And there's something called odd frequency superconductors. And those show up, and they satisfy exactly this property that under time reversal, you pick up minus the complex conjugate of these functions. And so just to show you some of the consequences of that, if you know about odd frequency superconductors a little bit, you might see the utility of this. All right, so let me say that again. Under parity, we see psi of k is equal to psi of minus k, but d of k is equal to minus d of minus k, right? But under time reversal, we only have psi of k goes to the complex conjugate of k, and then d of k goes to d complex conjugate of k. There's no psi of k goes to minus psi star of k. Right? And so we're asking what kind of states can do that? Or conversely, maybe I should call this, it's called psi tilde. Let's call this pi. Alright. And so the claim is that these are odd frequency superconductors. And odd frequency superconductors have been shown to give rise to a series of interesting effects near boundaries. In particular, we can imagine a situation where we have a conventional scaled singlet superconductor and a ferromagnet on one side. And then we can ask, how can we get a proximity effect of the S-wave term into here? And in fact, you can show that the coupling of psi s and m gives exactly something of this symmetry. And so you have an odd frequency state appearing in this particular case here. So in particular, you can write down a coupling term. And this is invariant under all symmetries, plus complex conjugate. I don't know, maybe I'm going a little bit too far aside with this. Has anyone here heard of odd frequency superconductors? Nobody has. Okay, one person has. All right.
You were telling it so beautifully.
Okay, so.
I find it still very, very confusing.
Yeah, well, that's because they look at the particular structure of the Cooper pairs in this formation without realizing this particular feature here. So it makes it harder to understand when you see these theories. So this tells you right away that if I have both psi s and m non-zero, this pi can be non-zero. And it turns out that in some situations, these odd frequency parts, as they're called, have very long coherence lengths. And so they can actually have a much longer decay into the magnet than the spin singlet part. And in fact, one of the consequences of this is you get this so-called long-range proximity effect that's mediated through this odd frequency channel, as they call it. So this is a way of understanding it. And the reason you don't have these in these states showing up within this weak coupling theory is because it needs to have some spin triplet degree of freedom, or some spin degree of freedom. And in fact, in the context of Kondo materials, people have looked at bound states of local magnetic moments and spin singlets. And these bound states together form these so-called odd frequency pairing states. And so in the Kondo business, there's a lot of, well, not a lot, but a number of people who consider these states.
So is there any bulk material in this type?
So it would be these Kondo materials that could exhibit them. And these, it turns out it's a difficult problem because these states are typically not weak coupling stable, as this would argue. So they have to be, you have to have stronger interactions, and then you always have the issue that if you have stronger interactions that stabilize the state, are there other competing interactions that might exist? And so we're not in the comfortable situation where we have these true weak coupling solutions that were guaranteed or stable in a certain regime. So, principle, they could exist, but at these, in this long-range proximity effect does exist. And so there's evidence for this odd frequency type states showing up in those cases.
So what if you have magnetic interface? Just
Yeah, you could create this, right? Yeah.
no, I mean not a have infinite interface, but just on the surface.
Yeah, well, that
a thin layer on the surface.
This has been done in channels, right? It includes single subconductors and
Yeah,
chromium dioxide, which is a half-metallic ferromagnet, and then it gets very long proximity effect. That is the claim.
Yeah, that's what they see. But you raise an interesting point. That could serve as a source for this, and then the question is how long is the decay of that into this other side? So are you familiar with odd frequency pairing states?
I do.
Okay. So maybe.
No, I'm just curious what happens if you keep the thickness of the ferromagnet very thin on the surface. Would that produce such states?
Oh, would that be a way of creating an odd frequency state?
Right, like like a thin layer next to the surface.
Yeah. Maybe. I don't know.
I mean, you just said it, right? That you need finite coupling.
Yeah, you have a coupling, but
And it's really like a proximity.
This is like a proximity.
Right? So you are in a ferromagnet, you have little choice. You don't really want to.
No, in half yes, but
Yeah, so the answer is no, it can't because you need this finite coupling. So it's fair to force a real support.
so I just presented that as something that maybe other people haven't seen. So it's okay if not everybody follows that discussion. All right. So those are the two things I wanted to say about symmetry. Now that we know the pairing transformations of the gap function, and we know the definitions of the particular representations, we can deduce where nodes must be by symmetry, and conversely, the weak coupling theory doesn't seem to allow every possibility, and so there are other possibilities in principle. All right, and so here I've shown you a series of particular spin singlet and spin triplet pairing solutions that you could get that correspond to each one of these symmetries. All right, and so here, in the singlet case, again, this is psi of k defined on the Fermi surface. And so singlet, you can just have it be constant. This particular A2G channel, well, it has the same symmetry as a KZ component, but you cannot write an even parity KZ component unless you write it this way here. This one you've seen, right? This is what I just showed you. This is the D-wave order parameter that we just talked about. This is just the same D-wave order parameter rotated by 45 degrees. And this is the two-dimensional representation. This is Kx, Kz, Ky, Kz. And as I mentioned, these are not unique choices, but they give you the right symmetry properties by looking at them. So there's, again, an infinite number of choices for each of these. And similarly for the spin triplet case, you can define something. This is actually in strong spin orbit coupling, so with respect to the point you mentioned. And then you get 4 different representations that are all one-dimensional. This one looks like a dot product between the d vector and the orbital component. And then you get a variety of other combinations. And this is the particular representation that we'll be interested in later, in particular this case here. So this is the odd parity, the d vector along the z direction, and then the kx and ky components. And so those two we'll look at in some detail. All right. What time did we start at, actually?
Oh, quite late actually, yeah, so
Okay.
just
Okay. So what I'm going to talk about now is go back to the original problem and then figure out what are the free energy coefficients from weak coupling theory. And so in that case, I'm going to focus on the spin singlet case because it's the easiest to show you the particular details. And I'll just sketch it because it's actually fairly involved to do everything. And so I'll show you the main points for that. So once again, with a BCS Hamiltonian, we do mean field theory, we get a self-consistency relationship. And the general approach to finding out the weak coupling coefficients, the easiest way is to look directly at this gap equation that you'll get from here. And the gap equation will depend on the order parameter, but you'll get the same gap equation when you minimize the Ginzburg-Landau free energy functional. And so what you do is you simply compare the equations that you get by taking the derivative of the Ginzburg-Landau free energy functional with respect to the two components of the order parameter to the same equations you get here from the gap equation. All right, and so the point then is to expand to find this gap equation to the appropriate order to extract the Ginzburg-Landau coefficients. That's the simplest and quickest way to get at these coefficients. All right, so to do that then, I don't know how many details I should go into here, but I'll give you some details. All right, so here is the mean field Hamiltonian rewritten in a slightly different form. This is just a constant. All right, this is a matrix, and then these are 2 fermion operators. But here I've written them as vectors, and so this is a 4x4 matrix. And the components of the vector are then ck up, ck down, c dagger minus k up, and c dagger minus k down. Right. We're going to make one assumption. So when we write down this matrix, that looks like the mean field gap term that we introduced as well. Now here as a 2x2 matrix. Here it's also as a 2x2 matrix. So the asymmetric part would correspond to the spin singlet, and the symmetric part to the spin triplets here. And this is also a 2x2 matrix, and this is also a 2x2 matrix. And so all we have to do actually is diagonalize this matrix to find the particular eigenstates of this Hamiltonian. And once we have the eigenstates of this Hamiltonian, we can calculate this expectation value of c dagger, c dagger. Right? And so one assumption that, in terms of the formulas written here, so if you ever want to look them up and use them, is that we use the assumption of a unitary gap, meaning that if I look at the product of psi dagger psi, this is just going to be a proportional to the Pauli matrix showing up here on the diagonal. So this is a diagonal matrix with all 4 components the same. All right. And so this is this is a 2x2 matrix. Sorry, so this is just with both components the same. Right. And so this makes things easier to solve because with this assumption you can just write down these solutions directly and get everything. And I should point out there are non-unitary solutions as well where this is not satisfied, and the solutions for that case are known as well. So you know all the possible solutions in this particular case. All right. So with this assumption then, you can then write down a matrix of u's and v's. This is the unitary matrix, and then you can apply the unitary matrix to the C's to get new eigenstates of your system, and then you can write your new eigenstates. You can write your Hamiltonian terms of new eigenstates, which are here, and then your new spectrum is given by this capital EK, and then the minus EK as well. And so we look at the structure of this capital EK. It's just the old kinetic energy term squared plus this thing squared. And this is what's really going to matter when we look at the mean field equations. So that was a quick sketch. Sorry?
This unitarity assumption, that is just a technical simplicity.
It's just a technical.
It's not that these solutions are more important in any way.
That's right. It's just a technical, it is just a technical simplicity. And I could have written down the solutions without this assumption, but they just take out much more space. All right. And so, here's the gap. This is the gap function. So this is corresponding to the quasi-particle gap that appears. And then in principle, the quasi-particle gap is k-dependent. But now, since I've diagonalized the spectrum, I can solve for this part expectation value here with respect to the mean field Hamiltonian. And the point is, the final result is this here, where everything depends on delta here, and this EK where the gap is given in here. All right, so this is going to be the starting point of where we find these phenomenological coefficients. All right, so everyone sees how we get there. It's, I think most of the steps are familiar to most people, possibly. Oops. Yeah, the rest is actually on the blackboard now. Maybe I'll write over here. All right. So let me just finish the steps of how we go from this equation here to the weak coupling coefficients. And again, these are going to be 4 simple steps. I'm just showing you the assumptions along the way. All right, so we're going to consider explicitly the singlet case. Okay, actually, one step beforehand. So, for simplicity, I'm going to consider no spin-orbit coupling. And that makes our lives a little bit easier, because that tells us the form of the spin dependence of this particular matrix here, right? I have 4 spin indices. So using no spin-orbit coupling will make our lives easier. You can do this without spin-orbit coupling, but the problems become a lot more complicated. All right. Actually, this is... well, so then you can separate the spin and orbital dependencies. And then these are known for both the spin singlet and spin triplet cases. Right? So I'm not going to write them down. And they're in the notes if you want to look them up sometime. But then we can turn to the free energy solution. In particular, I'm imagining I take this for the spin singlet case, and then I can describe everything in terms of this scalar psi k. And then we get the following gap equation. And then EK is this capital E written on the thing there. All right, and so again, the goal then is to go from this equation to the Ginzburg-Landau equation. All right, so let's show you the key steps. All right, so there's 4 key steps. The first step is we let VK K prime be written in terms of irreducible representations. And so we express it in terms of a basis, and you can always do this. Okay. So this corresponds to my particular representation, and if my representation has more than one component, m sums over those individual components. Right? And then this corresponds to my effective interaction for that particular pairing representation. So TC will be governed by this term here. All right, so that's the first step, and this will then choose this will allow for our particular choice of our order parameter here. We'll also expand this in terms of the same representation. All right, and then one step which was first done, well, I think a critical step that was done by Gorkov when he first derived the Ginzburg-Landau coefficients from recoupling theory. Well, maybe I'm wrong in the details here. But there's a very simple identity. Well, there's an identity that you can use, which is very important in carrying this out. So, to show you why I do this, we're going to want to expand EK in terms of powers of the gap, right? But we have the problem that this goes to 0 at places. As it goes to 0 at places, we can't expand the denominator. However, we can use this trick, where these are Matsubara sums, but you don't need to know that to use this trick, where we can then replace the tan h with E over E.
So this form of VKK prime is assumption.
No, you can,
The second line.
this is not an assumption. You can always decompose your VKK prime into particular different representations.
But then to be separate, like the product, the star independent K, if it's star independent K prime. So K
That's
on
completeness.
Yeah, it's a completeness relationship.
completeness
You can do this,
It's a
and we can
trivial.
talk about the details of that later.
So the K on is like the angle K on for the phi depend the psi depend on the angle K part.
You can think like pi limits,
Yeah,
That's
it's
just like
like
only the
the
angle
spherical
part.
harmonic.
but in this
completeness
case they
term.
couple to the spins.
Yeah, we can talk about the details of that, but you can do this. And I mean, the point is that this VK determines the structure of these individual basis functions. So that's what's important. All right. And so these are indeed Matsubara frequencies.
So I still think that the assumption must like for the rotational symmetry for VKK prime, because this one has to be based on some assumption.
No, it's
So the psi has to satisfy like a rotational symmetry, like the representation.
The represent-
basis
these-
of the rotational group.
no. These are representations that show up, and representations are irreducible representations are orthogonal, and so you can do this. We can talk about it in some more detail.
So exactly, you separate to say like. So this is really for any arbitrary V.
You can do
I'm not
this.
sure
You
if
can
it's
write it as
true.
a. Well, we can talk about it later.
If it's spherical symmetric.
Right,
I
yeah,
think
clearly,
for
if
the
it's spherical
rotation,
symmetric, you can see it, right?
Yeah,
In that case.
for the rotational system. For the
Two-body interaction is always spherical symmetric.
No, we're talking also about tetragonal symmetries.
No, but
Yeah.
that's the representation we're talking about.
Yeah,
But
yeah.
then you have on
Yeah,
the
so-
side, it's spherically symmetric, so it satisfies full symmetry.
So I'm asking, do we pose any condition on the form of V? So
By writing this out.
yeah, has it possibly satisfy, say, some rotational invariance? Is that the case?
Basis. So
That
you can do
that-
this
that I'm
decomposition
happy.
for
Yeah.
any symmetry.
you can do the decomposition for any symmetry because the
Yeah.
irreducible representations are orthogonal.
Yeah.
They are orthogonal basis choices.
I probably
So you can
think
do
I would
this.
agree, because like you still use the plane wave for the path, because it's still complete.
Yeah.
So that,
Yeah, exactly.
so even the
that's-
symmetry is not the Hamiltonian, it's not the symmetry of the Hamiltonian, but you can still use the basis to do the basics. I think maybe that's the case.
Yeah, well, we're expanding in irreducible representations of the group of interest, so that need not be spherically symmetric. It could have lower symmetry, but you can still do this.
I think it's-
Yeah, it's fine. But like I said, we can. So maybe if you saw the last lecture, I showed how to decompose. There's certain tricks you can do to do this. But anyhow, let's go on from here. Yeah. So what's the point of this expansion? Well, now E contains our gap, but the point is, and this may be known to some of you, is that we're going to be expanding near TC, and near TC, these omega n are relatively large compared to the gap, delta. The delta goes to 0 at TC, and this becomes in the order of TC. And so we're allowed to expand in this over this in this formulation. And so we can carry out that Taylor series expansion and get our linear psi and our cubic psi term from that. So that's the second step. Yeah, so this allows Taylor series. Since psi squared over omega n squared is much, much less than 1. All right. And the third is, how do we deal with this particular sum? Well, this is something you guys have seen, so maybe I'll make a couple comments though. All right, so we first write the sum as an integral over the density of states, and we average over surfaces of constant energy, right? Now, one thing you'll see here is my integral goes from a cutoff to a cutoff, and this cutoff is imposed by the weak coupling approximation. So we don't go from minus infinity to infinity, but instead we go from minus the epsilon c, which in conventional superconductors would be the Debye frequency, to plus epsilon c. And then we average over these surfaces of constant energy. And then we do one other thing.
Strictly speaking, this is retardation, right?
Sorry?
This is retardation.
Yeah, that's right. It is. But it's a way of doing it here. Exactly, yes. And then we do one other
So
thing.
closer to you see, you can basically forget the coupling constant, right? Because order perhaps always small.
Yeah, that's right.
Right.
That's right. Yeah, so that's the next. So then we also assume. So we assume further that this Debye frequency is much smaller than the Fermi energy, and if it's much smaller than the Fermi energy, we can take this out of the integral, since it'll be approximately constant, and put it here. All right? And so this becomes the density of states at the Fermi energy. And then we average whatever function we have on the Fermi energy. All right? And so with these two steps then, it turns out that now we can analytically do this integral. And so we can get rid of that, and we'll get left with things that are averages over the Fermi energy. All right, and then finally, the last step. Okay, so at this point then, we'll get an equation that looks like this. Average over the prime indices. Yeah, this takes a little time to write down. And so this is our gap function here and here. And so this is going to give a contribution to a linear term, and this will give a contribution to a cubic term. And I've carried out this Taylor series expansion that I talked about here. And so then, now I can do the final step. We now write down psi of k in terms of the order parameter, sum over m, psi gamma m of k. So we use these same basis functions here to expand. Whoops. I forgot the order parameter. So these particular etas are the components of our order parameter, and we expand the same basis function. And now we can use orthogonality of these functions to get equations for these particular etas. And then now that we have equations for etas, we can get equation for eta 1 and eta 2, and we can compare that to the derivatives of the free energy functional, and from that deduce what the fourth order coefficients are. All right. So that's the procedure of getting the free energy, and these are essentially the 4 key steps behind that. So So that should be enough to work it out now. Now I'll show you what happens in a particular example, in particular in the example of Strontium-Ruthenians. Alright. So let's skip ahead. So here now, here's our D vector, and I'm fixing it along the z-axis, because if you remember, I told you I haven't included spin orbit coupling, so in principle I'm not allowed to do this, but I'm going to assume that the TCs between different channels, the one-dimensional representations and the two-dimensional representation, are different anyhow, so that I'm confined to have my D vector along the z-axis. And then I have these two order parameter components, eta x and eta y. You don't need to say what fx of k is and what fy of k is, you just have to have the same symmetry as kx and ky. And also, we don't need to specify the Fermi surface, we just need to know we have some arbitrary Fermi surface. So, point is we're keeping arbitrary functions of k here and arbitrary Fermi surfaces because in principle we don't know what they are, right? We have to go to particular microscopic theory to see. Then you can go through this whole procedure like this, go through the expansion, and then you can find out that, whoops, I've gone from B's to betas, sorry about that. But you can then find out that beta 2 over beta 1 is given by a constant gamma, and then beta 3 over beta 1 is given by the same constant gamma, but 2 gamma minus 1, where gamma is the expectation value of fx squared times fy squared on the Fermi surface, divided by the expectation value of fx to the power 4 on the Fermi surface. And so the weak coupling theories are completely specified then by this parameter gamma. Now, I don't know, can anyone tell me an important property about this gamma? This
It's real.
it's real, yes. And then there's even one other property. It's bounded both above and below.
Yeah.
So actually, it's not so hard to prove that this must lie between 0 and 1. And that's actually very important. So,
Right, so this knows about the assumption that it's weak coupling and say conventional subconductivity emerging from a Fermi liquid.
yes,
Right,
that's
so
right.
when you would have a non-Fermi liquid normal state, you could have made a statement.
Yeah, then there would be different, exactly, yes, then there would be different. Yeah, this is, yeah, you've seen the assumptions. All right.
It's basically like assumption number 3, which is the one where you import from the liquid knowledge.
Yeah.
Right?
All right. So the next, okay, well, so I made the claim that gamma has to lie between 0 and 1, and it's actually not so hard to prove. Does anyone know how to prove it? Offhand?
I think I've seen the sketch of it. You complete fx squared, fy squared to a square minus whatever is left over, and you see from there.
Yeah, that's right. Exactly. You start from this. This expectation value is positive. And then we have the fact that we have the tetragonal symmetry, so we have to impose the condition, of course, like that. And that gives you the condition then that this must always be smaller than that. Alright, so that's important because that lets us show where in the phase diagram the weak coupling theories lie. And so that's what I'm showing here. If you look then at this condition, that means that all these theories lie along this line. So these are all the weak coupling possibilities you get for this particular order parameter. And you see in which phase they lie, right? They all lie in the kx plus iky state. And so you can understand that this is actually a fairly robust result. And what's interesting then is that maybe if you want to get non-weak coupling states, you can play with the fact that there's actually these points here where where this phase is actually degenerate with this phase. So right at this point here and right at this point here, these correspond to the points gamma equals 0 and gamma equals 1. You actually have a degeneracy between this 1I state and this nodal phase. And just so you can understand where that degeneracy comes from, it's easy to draw a picture so you can see it. Let me consider the following Fermi surface, perhaps a bit of a strange Fermi surface, but okay, so here I'm considering 2 dimensions because can draw dimensions. Consider a perfectly square Fermi surface. All right. Now let me define two gaps. Let me call this delta x and delta y. So these are constant over the Fermi surface portions here and here. And then you can see that the expectation value of fx squared, fy squared is what in this case? So I look at each point of k, what will I get? So in particular, delta x is only defined on this part, but not on this part. Delta y is defined only on this part, but not on this part. So what is this expectation value? 0. Right. And so this is going to correspond to the point gamma equals 0, which is this point here. So for this particular Fermi surface, you can get a degeneracy between the 1I state and the 1,1 state. And in fact, you can see that, right? In this picture here, the only way you can get this is if you have two uncoupled systems, ones which run one-dimensionally in this direction, and ones which run one-dimensionally in this direction, and there's nothing to couple their phases. And so there's no reason for the phase of the relative phase between delta x and delta y to be determined. And so the fact that there's an I here doesn't matter in that particular case. Right. So it turns out this is a little bit interesting in strontium-ruthenate because it actually does have these almost one-dimensional bands. Let me show you here. So these particular bands here, 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 well, they don't look so one-dimensional. Oh, here and here come from, to lowest order in a tight binding theory, come from one-dimensional poppings. And so you can imagine a situation, this is a two-band superconductor. Just for those of you who don't know details, this comes from XY orbitals. These regions come from XZ and YZ orbitals, these more or less flat regions. And there's some hybridization between the XZ and YZ orbitals in the simplest case. Right. But if we imagine this particular limit here, it turns out that there's a nesting vector that runs something like this. Right. And since I was giving these talks at Stanford, people were interested in pneumatic order parameters. And so just for fun, I said, well, such a nesting vector could give rise to a strain along the xy direction that could serve as some pneumatic order parameter. And so you could imagine that there might be a strong epsilon xy strain showing up here. And I won't go through the details, but now, if you add to your Ginzburg-Landau free energy functional a strain energy and a coupling between the strain and the order parameter, then, not surprisingly, you can find that you can tip the balance if you're in this region to go into this phase. And so coupling between some pneumatic order parameter and strontium-ruthenate, as long as it drives a strain in this direction, will push you down into this phase in principle. So you could get a line node phase if you're lying close to those boundaries. All right.
So I get it right that you have a hybridization between the two one-dimensional bands.
Yeah, you do.
And that should fight this.
That will fight this. And so that'll push you in this direction, but if the coupling between the strain and the order parameter is sufficiently strong, that can push you back down again, right? Yeah, so it's some circle around here. So you have to be in this region. But of course, there's a whole series of assumptions behind that. It's just for sake of argument. All right. Well, I think that's a good place to end, actually. I was going to go into the derivation of the spatial variation terms, but that unfortunately will take maybe another 30 minutes, if not more. And so at least this ends us at a good stopping point for this video. So I'll stop there.
So you mentioned the higher effects.
Yeah.
So the E plus IP or?
No, P plus IP.
P
plus IP. Yeah, so if people believe that is the ground state in strontium-ruthenate. And one of the reasons they believe it is this argument I showed you here, that it's, in weak coupling theory, is quite a robust state.